Good morning, everyone. I'm Miguel Artiega Varela, and I'm absolutely thrilled to be here with you all at the 34th International Materials Research Congress. Today, I'll be walking you through a recent first principle study on the structural, electronic, and optical properties of strontium magnetite, specifically focusing on its cubic perovskite phase. This is a material with huge potential for next-generation technology, so it's a real honor to dive into these theoretical findings with you today. Let's get right into it. Here's a quick look at our roadmap. We'll start with our introduction and objective, move through the computational methodology and structural results, then break down the electronic and optical properties, and wrap it all up with our conclusions. Section 1. Introduction and objective. So, strontium manganate, or SrMnO3. It's an incredibly fascinating material, right? Especially when we look at it in its cubic perovskite phase. But, as we all know, before we can actually harness a material like this for advanced technology, we really have to understand it fundamentally at the atomic level. And that was the main objective of this work. We set out to build a highly robust theoretical description of SrMnO3. By using density functional theory, we were able to computationally simulate its structural stability, its electronic behavior, and its optical response. Essentially, we're figuring out its true potential long before we ever have to synthesize it physically in the lab. Moving on to Section 2, Computational Methodology. For our calculations, we ran everything through the Siesta code, working entirely within the framework of DFT. Now, to make sure our predictions were solid across different mathematical models, we actually employed two distinct computational approximations. We used the generalized gradient approximation with the PBE functional and paired that against the local density approximation using the CA pseudopotential. Comparing these two really lets us cross-verify our results. But, before calculating any physical properties, we had to carefully optimize our parameters. It's kind of like calibrating a highly sensitive computational microscope. So we ran some pretty extensive convergence tests for both the basis set and the Munck-Pack K-point sampling to make absolutely sure our virtual environment was perfectly dialed in. Section 3. Structural results. After that rigorous calibration phase, we moved on to structural optimization via total energy minimization. And the equilibrium results were honestly super encouraging. Using the PBE approximation, we calculated an equilibrium lattice parameter of exactly 3.839 angstroms. When we looked at the CA approach, it shifted just a tiny bit to 3.879 angstroms. The big takeaway here is the incredibly tight alignment between these two distinct models. They're literally within a fraction of an angstrom of one another. This gave us a really beautiful validation of the cubic perovskite structure stability. With that structural baseline firmly locked in, we got the green light to dig deeper into the electronic and optical testing phases. Which brings us to Section 4, Electronic Properties. All right, so with the structure established, we mapped out the band structure and the density of states. And this was a real aha moment for our team. Under both the PBE and CA approximations, we observed a very distinct, undeniable overlap between the valence and conduction bands, happening exactly at the Fermi level. So what does this actually mean? Well, because these energy bands overlap, the electrons are highly mobile. They're free to move. This mathematically proves that cubic SrMnO3 acts as a purely metallic conductor. We found absolutely zero conventional band gap under any of the conditions we tested. It is fundamentally, intrinsically metallic. Now let's look at Section 5, Optical Properties. To figure out how this metallic perovskite interacts with electromagnetic radiation, we focused on the imaginary part of the dielectric function. Now, while that might sound a bit dense, it's essentially just a way to map exactly how the material absorbs energy across different spectrums. And the calculated optical response is just fascinating. We noticed two distinct behaviors. First, down in the infrared region, the absorption is heavily governed by the physical vibrations of the material's atomic lattice, so the vibrational modes responding to heat. But then, when we shift over into the ultraviolet and visible light regions, that absorption is driven entirely by rapid electronic transitions. By capturing both of these mechanisms, we get a really comprehensive visual picture of how this material handles light and heat. Finally, Section 6, Conclusions. To wrap things up, this first principles study really gives us a solid, comprehensive theoretical baseline for cubic SrMnO3. We validated its structural stability, pinning down those equilibrium lattice parameters at 3.839 angstroms with PBE and 3.879 angstroms with CA. We also consistently proved that it is a pure metallic conductor, driven by that key band overlap at the Fermi level. And optically, it shows a highly dynamic, multi-spectrum absorption profile. Because of this unique lack of a band gap,
gap combined with its dynamic light absorption, SrMnO3 isn't just a theoretical curiosity for us. It's a prime candidate for driving the next generation of high-efficiency optoelectronic sensors and advanced electronic devices. The really exciting question we're left with now is, armed with these ideal theoretical parameters, how quickly can we successfully synthesize this in the lab?
Thank you for your attention.